In this video, we will learn about the properties of bulk aggregates of molecules together in what are called compounds. The aggregation of molecules together is driven by non-covalent bonding interactions. This will also be referred to as intermolecular forces that are attractive. And finally, another term for this idea is supramolecular forces. All of these are involving things that bring individual molecules together. Of these forces, there's kind of three main forces that we like to think about. So the first of these is the van der Waals force, sometimes also classified as a London dispersion force. These forces refer to attraction and repulsion that arise from transient changes in electron density. In other words, given a molecule and its electrons around the atoms in that molecule, just at certain points in time, there might be an induced dipole where the electron density happens to favor one side of the molecule over the other. That induced dipole can then have an interaction with another dipole. So again, this dipole is temporary, but when it is there, it is exhibiting an interaction. And at all points, the electron density in all molecules is going to be kind of doing this transient changing and thus having this induced dipole and thus having a van der Waals force. To see what this looks like in a molecule, this is a model of hexane, and in the large gray kind of bulbous looking pieces out here, that's supposed to be kind of the overall electron density of hexane. So really when we're thinking about the molecule of hexane, we think about the fact that there are nuclei at the balls here, but that the electrons are really occupying kind of a nebulous region that looks like this. And that if you have a lot of different hexane molecules all together making up hexane liquid, then we have to think about a lot of things that are shaped like this kind of packed together. The next type of interaction or force we want to think about is the dipole-dipole interaction. And so this is different because now this is talking about interactions between permanent dipoles rather than induced ones. So when there's a permanent dipole, that means for whatever reason the molecule has a dipole in it. So for example, in a molecule of acetone, the carbon is exhibiting a partial positive charge and the oxygen exhibits a partial negative charge because you have the resonance form that looks like this. And that means that overall you get a permanent dipole in this molecule in that direction. What that means is that when you have multiple acetone molecules all kind of mashed together in a liquid, they will interact in a way that aligns these dipoles and places the positive end of one dipole with the negative end of the other dipole overall. And that would be the more stable way to orient these molecules together relative to each other. And the final type of interaction or force that's really important is that of hydrogen bonding. So by definition, hydrogen bonding is an interaction between a hydrogen atom that is bonded to an electronegative atom Z, and the interaction is from the hydrogen atom to the lone pair of another atom, in this case indicated as A. So an example of that would be if I take this ethanol molecule, and if I think about actual ethanol liquid, what I would see is that I would have a hydrogen bond here, so hydrogen bonding often indicated by these dots between a hydrogen and a nearby lone pair. So in the liquid ethanol, there's a lot of hydrogen bonding that kind of holds the molecules in that liquid together. To give you a sense of the scale of these forces, I think it's valuable to think about the fact that the van der Waals force might be at the kind of the 1 to 3 kilocalories per mole range. The dipole-dipole interaction might be a little bit higher at 2 to 5. And then finally, hydrogen bonding comes in a little bit higher on average at 5 to 10 kilocalories per mole. And so if you compare that to, for example, cyclohexane chair flip has a barrier of 10 kilocalories per mole. So about the same kind of amount of energy involved. And then if you finally compare that to, let's say, a carbon-carbon bond, now carbon-carbon bonds are getting you closer to 100 kilocalories per mole. Right? So really the definition of a bond versus a non-covalent bonding interaction is just the fact that the non-bonding interaction occurs at a much lower amount of energy. So much less stabilization is gained from this interaction, and there's just kind of a gray area where we decide that this is no longer a bond, but rather just a interaction together. So some of the physical properties that are altered based on changes in intermolecular forces between molecules are the melting and boiling points of a compound. So for example, if we look at the series of going from butane to pentane to hexane, and we think about the boiling point, the boiling point increases in temperature as there are more and more carbons in the chain. This makes sense if you think about it from a van der Waals interaction perspective, where in order for butane to boil, that means that all the adjacent butanes in a liquid need to separate from each other and enter the gas phase and become isolated. So when they're separating, that means we need to break those favorable interactions between butane molecules. And I think you can appreciate that a butane molecule should have less overall interactions than a hexane will, because hexane is larger and longer. So if I use my whole arms to do the interaction here. Another series, just to give you an example, would be to compare different types of forces that are involved. So a van der Waals force, we already know for butane, is holding butane together in the liquid. That gives you a boiling point of -1 degree Celsius. If you incorporate hydrogen bonding by turning this into a propanol, so roughly the same size of a molecule, but just has hydrogen bonding capability, because there's so much more interaction here, it's much harder to boil this molecule because there's much more stability that's gained by it staying as a liquid. Right? So if it's a liquid, it's gaining all this energy by being hydrogen bonded. If it's a gas, it has to give up all that energy. Somewhere in the middle is when you have a dipole-dipole interaction, and so a molecule like this one, so this is methyl ethyl ether, it has a permanent dipole because it's not symmetric, and there's kind of an overall dipole that follows the electronegativity of this oxygen. So then that means there are these dipole-dipole interactions which are going to be stronger than van der Waals forces, but not quite as strong as hydrogen bonding. So that's why its boiling point is in between that of butane and propanol here. So another factor that influences these trends is the fact that there is an entropy piece that's involved in all of our thinking about chemistry. So if we think about the phase transitions of going from solid to liquid and then liquid to gas, there's two different things that are happening. So all molecules will have electronic states of energy no matter what phase they're in. All molecules that have more than one atom in them also have some amount of vibrational energy no matter what phase of matter they're in. But as you go from a solid to a liquid, in the liquid you start to gain rotational entropy. So as a solid, a molecule can't rotate around because it's kind of fixed in place as a solid. But in a liquid now you can rotate, and so that's called gaining a degree of freedom. When a molecule has more degrees of freedom, that means it also has more entropy. So in general, liquids have higher entropy than solids because there are more rotational ways to distribute the molecule. However, that comes at the cost of losing a little bit of your intermolecular interaction. So in the solid, you can guarantee that the hydrogen bonds are taking place because they're kind of fixed in place like this. The two atoms have to be arranged as so, there have to be interactions. Now in the liquid, as molecules are rotating around, we kind of lose that interaction. You know, it might be there for 10 seconds, but then the molecule might rotate and you lose the interaction. So on average, we say we lose just a little bit of the intermolecular interaction. Now when we enter the gas phase, a molecule now goes from having this rotational degrees of freedom, electronic degrees of freedom, and vibrational degrees of freedom, to also gaining translational degrees of freedom, meaning that it can now move in X, Y, and Z much more significantly than it could as a liquid. But as we were mentioning before, in the gas phase we have to completely give up our intermolecular interactions. So we're sacrificing a lot of energy while gaining a lot of entropy. And so it's those kind of balancing factors that influence overall the trends in boiling points and melting points. So to give you a sense of how these two factors are interplaying with each other a little bit, here is a chart showing you the melting and boiling points for 3 structural isomers of C5H12. So on the left here is a very highly symmetric version, so this is called neopentane. On the right is the linear pentane. In the middle we have kind of the methylbutane, also referred to as isopentane. So again, exact same structural formula, which means the same number of electrons, same number of nuclei. However, they should exhibit changes in amount of intermolecular forces they can engage in and changes in the amount of entropy lost or gained. So if we're looking at the boiling points here, what we can see is that, again, they're the exact same molecular weight, but they have different boiling points. So the reason is that for a molecule like neopentane, if you imagine its kind of overall electron density, it's much more like a sphere and it's much more compact. So it just has less overall surface area to be interacting in kind of a van der Waals way. Right? So it has the lowest boiling point. The 2-methylbutane isomer here has a higher boiling point, but not quite as high as linear pentane, because linear pentane really maximizes the amount of surface area that can be interacting with other molecules. The melting point trend is a little bit more complicated. So what you see is that the neopentane here has a drastically higher melting point, right? Way higher melting point. And so that's actually because of the entropy factor. So this molecule is much more symmetric than the other two. And so when a molecule is more symmetric, it actually has less rotational degrees of freedom. In other words, if I take this molecule and I rotate it a little bit, it looks exactly the same, so I kind of lose entropy because of that overall symmetry. The reason for this is that temperature and entropy are closely related. As temperature goes up, we usually increase in entropy because that allows us to reach more different ways or energy levels in which we can distribute the various molecules in our system. But because there are inherently just less rotational ways of distributing this molecule, that means that increasing the temperature doesn't really gain us much entropy at all. And so then the intermolecular forces remain more significant than any entropy we could gain. So then our melting point becomes really high. It has to be really high in temperature for there to be enough entropy gained to override the intermolecular forces lost. So that's not the case for these two molecules because they don't have as much symmetry of the molecule, so that means they gain a lot more entropy as they go from solid to liquid, so then it happens at a much lower temperature. Generally speaking, the trends we'll see are that as there are stronger intermolecular interactions and forces, that will lead to, generally speaking, higher phase transition temperatures. And then, of course, as we just looked at, the higher the symmetry of a molecule is, the higher its melting point will be. Another important factor to consider is that we don't always think about molecules as just being a pure substance, right? So we're not always just thinking about a cup full of ethanol and just thinking about 100% ethanol. In reality, what we're thinking about most of the time is actually an organic molecule that's dissolved in a solvent. And so what that means is that we really need to keep in mind that there are all sorts of intermolecular interactions between the solvent and the organic molecule solute. To give you a perspective on why that's the case, well, it turns out that organic reactions are often conducted at this concentration of 0.1 molar of the reactant in some sort of a solvent. And if you go through the math, depending on the solvent that you're working with, that can lead to over 100 to 1, usually it's several 100 to 1 ratio between the number of solvent molecules in the reaction flask and the number of solute or reactant molecules in a flask. And so what that means is that in practice, your solute or your organic molecules that you're thinking about are actually fairly isolated from other copies of itself. It's mostly interacting with the solvent. And so just to give you an example of that, there's a cool feature of some molecules that's called solvatochromism, in which the molecule actually changes color depending on what you dissolve it in. So I'll give you the structure of a very prominent example, which is called Reichart's dye. So it has this interesting kind of charge separated structure like so. So you can take this molecule and dissolve it in all sorts of solvents, and what you get are an amazing different amount of colors depending on the solvent that it's dissolved in. And that tells you that the interactions between the molecule and the solvent are really changing somehow the properties of the molecule. So the color that is either emitted or absorbed by a molecule is related to an electronic transition. So in other words, an electron has to get excited from one energy level to another if it's absorbing light, and if it's emitting light, that electron then drops from a higher energy level down to a lower one. So it looks something like this. And so the color that we see in molecules is related to a process like this one on the left here, where the ground state of the molecule absorbs energy to reach an excited state. The energy gap right here is correlated. Well, that's the energy gap, and since E equals h times nu, or the frequency of light, that tells us that the frequency of light, or the wavelength of light that we see, depends on this energy gap. So it turns out, for reasons beyond us, that the excited state is less polar than the ground state. And so what that means is that if this molecule is in a more polar solvent, the energy of the ground state is lowered because there are more positive interactions, more favorable interactions between the polar solvent and the polar ground state. So the more stable the ground state is in energy, the lower in energy it will be on this chart. And the larger the gap between the ground state and excited state, the smaller the wavelength of light, or the higher energy wavelength of light, is needed to be able to excite the ground state to the excited state. And so what you're looking at again in this nice colorful picture is that molecule dissolved in different solvents. So I'll show you a few of the structures here. So on the very left is 1,4-dioxane. Looks like that. Right next to it is chloroform, so that's CHCl3. A couple solvents over is 2-propanol, or isopropanol, or rubbing alcohol. Next to that in purple there is ethanol. And then finally on the very right is water. And this trend, if you're looking at this, hopefully you're able to see that this goes from very non-polar. This molecule dioxane actually doesn't have any permanent dipole, all the way to extremely polar because there's a permanent dipole and hydrogen bonding present in water. So this is just one example, and kind of a unique example, but the point is that solvent molecules can really influence the stability and the properties of a given molecule. The forces that we just mentioned are also important to think about within a single molecule, so not just between separate molecules, but also within a single molecule in what's called an intramolecular interaction. An example of this that works really nicely is to look at 3 different structural isomers of hydroxy benzoic acids. So isomer A here has a melting point of 158.6 degrees Celsius, and then for some reason isomers B and C now have much higher melting points. And so at first glance you might look at this and wonder, well, they all seem to have hydrogen bonding interactions. Well, why is there such a drastic difference for isomer A? So if we look at isomer A, it can exhibit an intramolecular hydrogen bonding interaction that I've shown here in red. If you look at the way this hydrogen bonding works out, it makes a really nice 6-membered ring right here. So this is a very common motif that shows up. Intramolecular interaction that happens in kind of a 6-membered ring organization. If you look at, let's just say, isomer B, if it wants to gain the stability of interacting in a hydrogen bond, it needs to do so with a second molecule of itself, right? So you need to have 2 molecules in order to form that hydrogen bond that is supposed to be lowering the energy of the system. Okay, so in both cases, in molecule A and in molecule B, as a solid, there should be hydrogen bonding. So they should have roughly the same amount of intermolecular force that's gained. When we melt, we have to lose some amount of those intermolecular forces because we have to separate them in order to allow for some of that rotational movement in the liquid. However, in molecule A, even if you separated molecules A from each other, they would still be able to participate in hydrogen bonding within themselves. And so that means you never actually lose all that energy gained from hydrogen bonding. So that means that it's much easier to then do melting because you're not sacrificing as much of that hydrogen bonding interaction. For molecule B, however, all of its hydrogen bonding has to happen intermolecularly. So then melting means that you lose all of that energy, so you need a lot more temperature to be able to get that melting to happen. Finally, for isomer C here, we see that its temperature is a little bit higher for its melting point, and that's likely because it has an increased symmetry in the molecule relating to the entropy factor. Alright, so that was the influence of structural isomerism on some of the molecular properties that we care about. Turns out that stereoisomers also exhibit some of these trends as well. So our rules will look like this. Basically, diastereomers are essentially just different molecules in terms of properties. They will always have different physical properties. So melting points, boiling points, viscosity, density, all of that will be different between diastereomers. Enantiomers are a different beast. They will have identical physical properties unless they are within a chiral environment. So a really important example of this is tartaric acid. And so I have the 3 possible stereoisomers of tartaric acid shown here. So if we look at those melting points, indeed, the enantiomeric pair right here have the exact same melting point. The meso stereoisomer has a different melting point. And so a tricky example is to think of when there are chiral environments. So some examples of when there is a chiral environment would be, for example, in the human body. So all the enzymes in our body are acting in by creating a chiral environment for a molecule to react, which means that two different enantiomers will react differently when they're inside the same enzyme. Another possibility of interacting with a chiral medium is when you have what's called optically rotated light. So it turns out that light has kind of this rotation to it, and normally if you're dealing with light, what you're seeing is both rotations canceling each other out, so overall you don't see a rotation. There's ways to intentionally get just a single rotation of light, and when you do that, this light is now chiral, and because the light is chiral, then it interacts with enantiomers differently depending on which enantiomer the light is interacting with. So this is a nice experiment then for being able to figure out exactly which enantiomer of a molecule you happen to be dealing with. And so the value that's detected is called the optical rotation. And so essentially this reflects how much the light is kind of deflected away from its rotation by the enantiomer. So for an achiral molecule, that's going to be 0 because there's no difference one way or the other. It doesn't matter which rotation of light is hitting the molecule, you're going to get the exact same result. For one enantiomer or the other, you're going to get the negative or the positive. So this sign right here tells you exactly that you have one enantiomer or the other. It's important to understand that the sign doesn't mean anything about which enantiomer. In other words, the sign doesn't tell you if it's an R or an S compound. It only tells you that you have an enantiomer. So historically, this was essentially the only way for people to determine whether or not they had enantiomers or whether or not they had pure enantiomers. And so what they were looking for here is that optical rotation, which they called optical activity. A final important concept is to think about what happens if you mix enantiomers together in a kind of a 50-50 mixture, so exact same amount of both. When that happens, that's called a racemic mixture. So you have 50% of one enantiomer, 50% of the other enantiomer. When you do that, because it's a mixture, the melting point changes. So in this case, it goes way higher. And because half the molecules are rotating light by this negative 12 degrees, the other half are rotating the light by a positive 12 degrees. Overall, if you measure the optical activity of a racemic mixture, you'll get a value of 0. So again, the point here is that diastereomers are always different. Enantiomers are going to be the same unless they're within a different environment. This is especially relevant as a concept to people interested in studying biochemistry because historically a lot of the names for molecules were assigned by using the optical rotation to give the stereoisomerism because they didn't have the tools to actually know what the structure was. So they didn't actually know if it was going to be an R configuration or an S configuration. So many biomolecules are actually named this way, using the optical activity, so a minus or a plus sign. Or they would also kind of substitute minus for a D for some dextrorotatory, or L for positive, which is levatorotatory. Again, these have no connection to R or S. These are only connected to the experimental measurement that is here. You'd have to be given this number to know this piece of it. Finally, when you have a racemic mixture, it is very common for people to use this plus-minus nomenclature right here to indicate you have both the positive rotating and the negative rotating enantiomers. Another important concept in organic chemistry is the idea of taking a mixture of different molecules and separating them out into their pure forms. You should think that this should make sense because if you're taking a drug molecule, you definitely want it to be just the drug molecule and not some contaminants. If you're putting fuel in your car, you definitely want it to be just the good fuel and not the bad stuff that can burn your engine. And so this is extraordinarily important both in an analytical sense and in a preparative sense in the laboratory. When we say analytical, what we mean is that we need to be able to detect whether or not there is a mixture in the first place. And when we say preparative, what we mean is we need to be able to make and purify large amounts of important chemical products. So common methods for separating mixtures of molecules are these three right here. The first one is crystallization, and so that's when you take something that's a solid and then do some manipulations to get it to form nice crystals. Turns out that crystals, because they're highly ordered, tend to be pretty pure because you can really only make something nicely ordered if it's only got copies of itself repeating over and over. Another technique is distillation. So this is useful for liquids. This takes advantage of the fact that liquids often have different boiling points. And so if you take a mixture of liquids, boil it up or heat it at one temperature, then some of the liquids will evaporate, leaving behind the higher boiling point ones. And then you can raise the temperature and then evaporate the remaining higher boiling ones. Then you have two separate collections, right? So distillation is very important in the alcohol industry where you're distilling alcohol out of water. The third, and probably the most important technique for organic chemists, is chromatography. This is when molecules are sent through a medium, and these molecules interact with this medium in a way such that they flow through at a different rate, so that at the end of the medium you can kind of collect whatever is coming out at that period of time as a hopefully purified sample. So on the more technical side, the way chromatography works is your mixture is first dissolved in a fluid called mobile phase, and that mobile phase, so this is a solution, is then passed through what's called a stationary phase. And so the stationary phase is what the molecules in chromatography will be interacting with. So depending on how much interaction there is between your molecule of interest and the stationary phase, that will determine the rate at which it goes through the entire chromatography system and comes out the other side. So one of the more important analytical chromatography techniques in organic chemistry lab is what's called thin layer chromatography, or TLC. What's happening here is we have a very thin plate that acts as the stationary phase, and the mobile phase kind of travels up the plate. This plate is usually a polar silica gel. So again, the plate, the stationary phase, is very polar. And so the other piece of chromatography is the mobile phase, and normally for organic chemists, the mobile phase or eluent is varied or changed to find kind of this optimal flow rate to be able to so-called separate different products on the TLC. Common eluents for organic chemists are these three right here. So most commonly we'll see hexanes with an S to indicate we're dealing with different structural isomers of C6H14. Dichloromethane, and ethyl acetate, which is this line angle drawing here. So I want to show you how this works with a video. So this is going to be a TLC that's being run of some extract from a plant. So what you're looking at is the extract being spotted on the TLC plate at the baseline level right there. So that's that green spot 3 different times. And that TLC plate is then placed into a beaker, where at the bottom of the beaker there is the liquid eluent. And as you know from putting any kind of dry substance into water or anything into an eluent, the eluent will kind of flow through the stationary phase, and in this case it's traveling up the plate. And as it travels up the plate, you can see differently colored compounds being separated. So they're traveling at different rates. Some of them travel just as fast as the eluent or mobile phase, and some of them travel slower than the eluent or mobile phase. And as time goes on and more distance is traveled, then you can see more and more of a difference between different molecules that are present in that initial mixture that was spotted onto the plate. So some trends we'll see are that if you're always using the same stationary phase and the same eluent, then a molecule will always travel the same RF, where RF is the proportion between the molecule's distance traveled and the eluent's distance traveled. In general, because the silica gel is polar, that means that more polar molecules will travel more slowly in the eluent, because the polar molecules are going to be interacting more with the silica gel. Nonpolar molecules will travel very fast, go straight to the top of the TLC plate. Finally, when we change our eluents to become more polar in nature, that will increase the RF value of all molecules. A tempting thing to think is that only polar molecules become influenced to move more quickly by polar solvents or polar eluents, but that's actually not true, because what you're doing is actually just only thinking about the stationary phase. You don't think about the interaction between solvent and solvent so much. You're really focusing on the interaction between the molecule and the stationary phase. And so if it can't tell the difference between stationary phase and mobile phase, then it's just going to travel quicker because it's spending less time in the stationary phase, relatively speaking. So in this example video of a TLC, we can kind of see that there are multiple different bands. So let's take a look at what these extracts are in the plant. So the very top there, the molecule with the highest RF value turns out to be called beta-carotene. Its line angle drawing looks like this right here. The fact that it has the highest RF value should tell you that it's the most nonpolar substance that was in this mixture that was spotted on the TLC plate. And indeed, if you look at its structure right here, this is a pretty nonpolar structure. In fact, it's just carbons and hydrogens. There's no electronegative atoms to create any permanent dipoles. And it's actually a very symmetric molecule, so there's no dipole at all. So it's really only going to be interacting through van der Waals interactions with the stationary phase. That means that it should travel very quickly with the mobile phase. Two of the greener spots, or greener bands in the TLC are chlorophylls. In this case, we're going to be able to identify chlorophyll A and chlorophyll B. So I have those structures here. And so if you're looking at the actual TLC plate, the two bands, there's kind of a more turquoise one that's a little bit more nonpolar or higher RF value. And there's one a little more green that is lower in RF or more polar. So if you're looking at these two structures, there's a lot to go through here, but at the end of the day, there's almost no difference. All this stuff out here is exactly the same. The only difference between these two structures is in this position right here. So chlorophyll A has a methyl group, chlorophyll B has an aldehyde. Chlorophyll B having an aldehyde, this extra piece of a dipole that's in the molecule, kind of a permanent little bond dipole right here. That is enough to change the polarity of these two molecules to be enough to detect on TLC. And because we expect that having this dipole in this molecule and not in that one should lead chlorophyll B to be just a little bit more polar, we would predict that chlorophyll B has that more kind of olive green color, and that's exactly the case. This is the higher polarity compound. It doesn't travel as much on TLC. It has a lower RF value. So in this video, we went through how the structure of a molecule can influence its physical properties and how its interactions with its environment can change aspects of its stability and aspects of its observable properties. Finally, we saw how we can take advantage of some of these differing interaction strengths and forces to take a mixture of substances and purify them to be able to isolate single compounds out of a crude mixture.